Hi, I'm David.
I'm Jan.
Jan. Yeah, we are physics majors. We're doing a project for our condensed matter class, and we are going to try to make glass shatter with sound waves. So basically, what we need to do is find the resonant frequency of the cup and produce that frequency with this function generator and amplify it so that we can get the molecules in the glass to separate, vibrate, and hopefully crack. So we are going to use an oscilloscope program that we got from Rutgers. We set it up, and basically all we need to do is pick up the vibrations with the microphone and find the peaks that come up the highest. So if you average out the peaks, you basically start getting what are the overtones and the fundamental harmonics that can be heard. The largest peak right here, which can be seen at around 1400 hertz, is what we know as the resonant frequency. All these other peaks are overtones. They are what is heard when basically anything vibrates. So even a guitar, if you vibrate a string of a guitar, what you hear are these peaks. So if you can produce that resonant frequency, you can actually get the molecules and the whole lattice to vibrate, and if it vibrates enough, you can actually break the bonds. The basic setup for this, we have a function generator, which creates a sound wave attached to a voltmeter, so we can measure the frequency of that sound wave. All of this attached to a speaker, so that sound wave can be amplified and channeled to, or funneled to the cup. This is all picked up by our microphone, which is then transmitting data to my computer, which is functioning as an oscilloscope.
We're going to use two different cups with different size and thickness, and we're going to try to make them vibrate and maybe shatter with sound waves at their respective resonance frequencies.
Alright. Dude, it's moving.
Yeah.
You see it moving, dude? Yeah, look at the cup.
So, it's pretty frustrating that our speaker isn't loud enough to actually crack the glass, even though we got a thinner one and it can vibrate a lot more. So to let out our frustration, Ron and I are going to crack this bad boy on our own.
Yeah.
Felt pretty good.
Hell yeah. Going down.
Our next victim. Woohoo! Woohoo!
Good time for me to answer.
Do you want to break a glass?
Yeah, well, no.
Hold on.
If you want to.
This is for all the pain you caused me. This is for all the pain you caused me, right?
The effect of resonance frequency can also be seen in large-scale structures. It was demonstrated in dramatic fashion in the collapse of the Tacoma Narrows Bridge. The bridge was found to sway in windy conditions previously, and it finally collapsed in 1940. It is believed that the collapse was due to the force of the wind contributing a perpetual driving force whose angular frequency matched that of the natural frequency of oscillation of the bridge. In this case, the power transferred from the force of the wind to the bridge approached a maximum, since the force of the wind and velocity of the oscillating bridge were both in phase, resulting in increasingly large amplitudes and the ultimate destruction due to poor safety features.